Dear students, the topic is relativistic Doppler effect. You are familiar with the Doppler effect in the classical for the sound. Here we will look into that effect, the Doppler effect in relativistic level. So topic code is the EMREL-S6. Now let us consider a source S emitting light having the light speed c. Let the source S moves with a uniform velocity v towards an observer O prime in reference frame 2. Let t prime be the time and v nu prime be the frequency observed by the observer O prime, which is called the observer in the moving frame. These are the two observers. This is the reference frame 1 and this is the reference frame 2, and this is the source which is moving with the velocity v. This source has a light, obviously, which has a speed s, which is a c, and takes the time t prime to reach at a certain point. Similarly, the same way the source is also moving with the velocity v, which is also relativistic velocity. Now this observer will observe the time as a t prime, frequency of that the source as a nu prime, while the lambda is c by nu prime. So reference the frame 1 observer will observe the time of this time as a t, frequency as a nu, and the distance will be observed here by the other travel total v times t. So let now the t prime be the time and v nu prime be the frequency observed by the O prime observer. Let now an observer O in reference frame 1, which is stationary, is observing this whole event and observe t time and nu frequency of the source being as observed by the O prime. Since this t and nu is the time and frequencies observed by the observer O, actually the same the observer O prime, which was also observing. Since the speed of the light is independent of the source, is a constant in all inertial frame of references, the wavelength lambda observed is given by lambda is equal to ct prime minus vt prime. So that is the ct prime is the, if you see from here, this is the total ct prime, and this is the amount of velocity with the velocity v, vt prime, which is the total distance. The lambda is left, how much is the total one wavelength. If some frequency is being generated, then the wavelength will be equal to ct prime minus vt prime. So where the lambda is the distance traveled by the light t prime minus vt prime, since t prime is equal to 1 over nu prime and t is 1 over nu, so lambda is equal to c by nu prime. So from the equation 1, what we have, lambda is equal to c minus t. This was the equation 1 here, this one. So taking the t prime common, so putting lambda is equal to c by nu prime, c by nu prime is equal to c minus v. This is the velocity of the source which is moving with this velocity, constant velocity, obviously, t prime, and that is equation number 4. But according to the Lorentz transformation, for relativistic time, t prime is gamma times the t. This is equation number 5. So putting that the value of the t prime, we get c over nu prime is equal to c minus v gamma times t. Rearranging, we get the this equation is rearranged, putting the value of gamma, which is 1 minus v by c whole square, and rearranging we get what, the nu prime, which is the frequency observed by the observer, is equal to c plus v by c minus v square root into gamma, where gamma is the nu prime is the Doppler frequency when the source is moving. So that is the or we can vice versa, we can say gamma is equal to c plus v divided by c minus v under the root. So the new Doppler frequency as observed by the observers, two observers, nu is obviously the frequency of the stationary observer outside. That will be, it will see a Doppler shift, but it will, the difference of the ratio of the difference of the two velocities, that is the speed of light minus the v and speed of light plus v, that is the ratio square root, that is the times the nu. R nu is equal to vice versa, we can say nu is equal to, we can put it, let me put that equation as well. Okay, here is the other way, that is the same frequency observed by the observer, stationary observer, is given by equal to c plus v divided by c minus v whole square root into nu prime. So that is the Doppler effect in the relativity, special theory of relativity. So the, what we have, the, that is the Doppler effect in special theory of relativity. So with this we reach to the end of the topic. Thank you.